Hi everyone.
Good evening.
Hi, how are you doing? Let's wait until 8:05, then we start our this week's content.
I won't be here on the lab for Friday. Um, is it very important? Like,
Um, just as usual, I will walk through the lab notebook.
okay,
So you can still watch the recording. If you have further questions, just feel free to send me an email.
okay, thank you.
Okay, let's get started. So in this week, we will finish up the supervised learning. So basically, we will finish the evaluation part for classification and talk about the last simplest classification model that would be the K nearest neighbor. And then we will get into the new section that is unsupervised learning, and we will learn about the k-means clustering method. So many people get confused with the classification method, k-nearest neighbor and k-means clustering method. So we put them together to so that you can understand the difference among them. Okay, so let's first finish the classification evaluation part. So you have worked on the lab notebook for week 2, and in the notebook you have experience about evaluating the classification model performance using accuracy as the measurement. That's the most common measure we are using to evaluate classification performance. And there are some other uh, evaluation measure. And when we're focusing on different aspects of the model performance, we will use other measurements. But let's start with this, the most common and widely used accuracy measure. So for classification task, we got prediction and we have true labels. So we may compare the model prediction and true label to see if the prediction is correct or not. And then we can get this um, classification errors. So that is the count. So it is counting how many predictions that was made wrong. So the incorrect classification number divided by the total number of samples or the total number of predictions, and the result will be the error rate. And if we use 1 minus the error rate, that would be the accuracy. Or we can write like, uh, say, correct prediction. We can count the correct predictions and divide it by the samples. And there is another way to write the equation. So they are totally equivalent. So we now know how to calculate the error rate and the accuracy. So these two measurement the most commonly used measure, but they are not meaningful in class imbalance problems, especially in like medical field. In that case, we have less patient than the healthy people. So the data will very imbalanced. So in different scenarios, we may need other measurement to help us to reflect the performance of the classification model. So let's just review the classification, binary classification. So for binary classification task, we have data and we have data with feature, and that's the input variables. And we provide data labels, and that would be the true label we are going to predict with the model. So in this case, uh, the true labels um, differentiate using different colors. So we will treat the red color data points as positive samples, and we treat the blue data points as negative samples. And after we train the classification model, the model will give us this dash line. This dash line is a separator, and we will make prediction based on this separator. So for the data points on one side of the separator would be either positive prediction or negative predictions. So that is the result, the input and result we will get from the classification task. And based on this fact, we introduce a few terms that will reflect different aspects from of the classification result. So because we have predictions and we have true labels, and we have both positive prediction and negative predictions, and we have positive label and negative labels. So combine these four situations, we will get four terms. So false negative, true positive, and true negative, and false positive. So if you have learned statistics, you may have learned this kind of concept. So false for false negative cases, all these four terms count. So they are counting different cases. So for false negative, it refers to negative prediction, but this prediction is wrong. That means the data point that was positive sample, but the model predicted as negative prediction. And so this prediction is wrong. So that's why it's called false negative. And the true positive is straightforward. So the model predicts the data sample as positive case, and the data point is actually a positive sample. So the prediction is correct. So that's it. That is true positive. And true negative is also straightforward. The model predicts the data point as negative sample, and the data point is actually negative sample. And so the prediction is correct. So that is true negative. And for false negative, that means the model predicts the data sample as positive sample, but this prediction is incorrect. The data sample is actually a negative sample. So that is this data point will be counted as false positive. So all these four terms representing counts for different cases. And based on these four terms, we will get uh, some more advanced measurement, that is true positive rate and false positive rate. So you will see a few slides later that the true positive rate is also called recall. So it is calculated as uh, the number of true positives divided by the sum of true positives plus the false negatives. So the number of true positives, that is all the right points below the separator, and the false negatives that are uh, the red point on the wrong side of the separator. So that means the denominator is the total number of positive cases, positive data samples. And for false positive rate, the numerator is false positive, and the numerator is false positive numbers, and the denominator is the sum of false positive and true negative. So that would be the false positive is the blue point on the wrong side of the separator, and the true negative are the blue points on the correct side of the separator. And both of them the total number of negative samples. So that is the true positive rate and false positive rate. So what are these two measurements used for? These two measurements are going to answer questions like, um, let's say for medical diagnostics, um, it will answer like what percentage of sick patient do we detect? So that is the true positive rate. And for question like what percentage of health people are wrongly flagged, that would be represented by the false positive rate. And here are the definition for the true positive, true negative, false positive, false negatives, these four terms. And for false positives and false negatives, the false positives are also known as type 1 error, and false negatives are also known as the type 2 error. And these two terms are more commonly referred in statistic fields. So knowing these four counts, we can organize them in a matrix. And this matrix is called confusion matrix. So for each row, the row are representing the predicted values. So the first row is representing the positive predictions, and the second row is representing the negative predictions. And the columns are representing the actual values. So that is our true label. So the first column is representing the positive data samples, and the second column is representing the negative samples. So we just put the corresponding term, like true positives, to the corresponding cells. So let's say, for example, true positives, that means the prediction should be uh, positive, and the prediction is correct. So that means the true label should also be a positive sample. So that means the row should be positive and the column should also be positive. So this true positive number should be entered here. And the the other three terms are following the same rules. So we just put the corresponding count into the cell, and this will form the confusion matrix. And later on, we will see more measurements that is computed um, based on this confusion matrix. So it is more intuitive way to visualize I would say the summary of the classification result. And is another example about using the classification model to classify the input image as either cat or dog. So cat, it would be treated as positive sample, and the dog is treated as negative samples. So we have actual values. So this would be the data true label, and the predicted values are the outcome from the model. So this is the prediction from the model. So we can compare the true label and the prediction and count the case numbers for each situation and put the count numbers into the confusion matrix as different cells representing like true positive, false negative, false positive, and so on. Okay, you may notice that the row now is representing the actual values and the columns is representing the predicted value. So it doesn't matter if the actual values is on row or dimension or on the column dimension. So it's all right as long as the count number put correctly into the corresponding cell. Okay, there's okay. Let's see how we can calculate the accuracy based on this confusion matrix. So accuracy is a valid choice of evaluating for classification problems which are well balanced and not skewed, or there is no class imbalance. So as we have seen in the first slide, so the accuracy can be calculated as the correct predictions divided by the total number of samples. So here, so how can we get the total number of correct predictions? So that would be the true positive and the sum of true positive numbers and the true negative numbers, because only these two cells representing true prediction. So that means correct predictions. And false negative and false positive are representing the incorrect prediction numbers. So we can use 6 plus 11 divided by the total number of predictions. So the total number of predictions could be get from like summing all the values in these four cells, and we can get the accuracy number. So just note that the application of accuracy measure would better suited for well-balanced and not skewed data set. So there's no class imbalance. Okay. And the next measurement would be precision. So it is also called true positive rate. Precision is defined as the ratio of the total number of correctly classified positive classes divided by the total number of predicted positive classes. or out of all the predictive positive classes, how much we predicted correctly. So we are expecting the precision should be high, and the maximum value for this precision should be 1. That means um, the model predictions, um, make positive predictions, and all these positive predictions are correct. So in that case, the precision is 1. So it is a useful metric in cases where false positive is a higher concern than false negatives. So let's think about a scenario that, let's say, spam detection. So it is a classification task. We have seen it multiple times. And email will be treated, email that is spam email will be treated as positive cases, and non-spam email will be treated as negative cases. So if the model make positive prediction, that means the model treat the email as spam email. So in this case, we would expect high precision. So that means whenever the model flags an email as spam, it's almost certainly the email is a spam. So um, we can so that is scenario that precision would better reflect the performance, and the precision is calculated as uh, prediction actually positive. That is the true positive number divided by total predicted positive. So that is the true positive plus false positive, because all these two cells are representing the positive predictions. So if we add them together, it will represent the total number of positive predictions. So so let's get back to the email example. So we have known that when precision is high, that means the model flags an email as spam. The email almost certainly be a spam email. What if the precision is low? That means many important emails would be wrongly flagged as spam, and it will be put into the spam folder, and you will never see the important email again. So that is not acceptable. That is not acceptable at all. So we are expecting high precision in this scenario. And the next measure would be recall. So recall is defined as the ratio of the total number of correctly classified positive classes divided by the total number of positive classes. So, or we can say out of all the positive classes, how much we have predicted correctly. So recall should be, we are expecting recall should be high for ideal model, and the maximum value for this recall will also be 1. So in that case, all the actually positive data samples are detected um, by the model. So recall is a useful metric in case where false negative trumps false positive. So let's think about so let's look at the equation first. So it is calculated as the predictions actually positive. So that is the true positive count divided by the total actual positive. So the total numbers in the first row will be all the actual positive data samples, and the number will be the recall. So let's think about a scenario like disease screening, for example, cancer detection. So recall is more important than let's say precision or accuracy, be because we want to catch as many true cases as possible. So even if it means some healthy people may be flagged as sick people, but these people can go through further testing to be corrected. But missing real sick people is far more costly than a false alarm. So in this kind of situation, recall is a better measurement to reflect the model performance. So in comparison, like if we're comparing precision and recall, so in situations where false positive are costly, let's say spam email detection, we will prefer precision because we don't want important email to be flagged as positive spam email. And for situations where false negative are costly, like medical diagnosis, uh, where we want to find out all the true true positive or true sick patient, even if we may misdiagnose some healthy people, but it is acceptable. In such kind of situation, we will prefer recall over precision. And is there another measurement that can like combine the advantage of both measurement of precision and recall? And that would be F1 score. So the F1 score is a number between 0 and 1, and it's a harmonic mean of precision and recall. So we use harmonic mean because it is not sensitive to extremely large values, unlike a simple average. So F1 score sort of maintains a balance between the precision and recall for the classifier. So if the precision is low, the F1 is low. And if the recall is low, the F1 score will also be low. So it kind of using the F1 score uh, would maintain a balance between the precision and recall. Because normally, if we tune the model to achieve better, like say, precision, um, we may make the recall lower at the same time. So it is a trade-off between precision and recall. So F1 score maintain could show intuitive a view about the balance between precision and recall because measurement, if either measurement is low, the F1 score will be low. So that's F1 score. So it heavily penalized the extreme imbalance between precision and recall. Um, so when the F1 score is high, that means both precision and recall are reasonably good. Okay, that would be the some evaluation measurement for classification result. Any questions till now? All good. So
Um, Quick one. Is F1 score correlate closely with accuracy because it's sort of going to go diagonally and looking both sides?
uh, ac in some scenario, accuracy cannot reflect the true performance of the uh, classification task. Because let's say for medical diagnosis, sometimes let's say we have 100 people, and 99% of the people will be patient, and only one people will be healthy people. And if we have a model that can only make negative prediction, so it will treat all the people as um, uh, I make it wrong. So 99% are healthy people and 1% is the patient. So if the model always make positive negative prediction, so it treat all the people as healthy people, for the accuracy, uh, let's say accuracy can achieve 99 over 100 because it make this only one wrong prediction, right? So it can still achieve 99% accuracy. It seems high, but it doesn't serve the purpose of our uh, diagnosis purpose, right? So um, we can tolerate like two or three healthy people classified as patient, but we cannot tolerate that this only patient diagnosed as healthy people because this delay of the diagnose or detection will be make the treatment more costly in later stage. So it is not tolerable. So in this case, accuracy is not acceptable. And if we calculate the precision, no, if we calculate the recall is zero, right? If the recall is zero, the F1 score is zero. So F1 will be zero. So you can see that it is not correlated
I see.
for imbalanced data.
Okay. So it depends on the data. It doesn't, well, not, there's no one metrics better than the other. It depends on what we're trying to find out.
Yes, yes, and the characteristic of the data set.
Sure.
Okay.
Thank you.
Now let's get into the one naive classification method, and people often get confused about this k nearest neighbor and k means method we will talk about later. So this is a classification. This is a classification method. And of course, it is a supervised learning method. So you can see from the input. So we got feature vectors x1 to xn. And so that means we have n data points, and each data point or each data sample come with d dimensions. That means each sample has d features. And we also provide labels for each sample. So that is supervised learning, right? And it is not continuous values. These labels are representing the group index. So it is a classification task. So if we just draw all these data samples on a 2D space, we can see the distribution of the data set and their group belongings. So how to, if we are given a new data point, let's say this star called X prime. So how can we classify this new data? So which group should this data belongs to? With the k nearest neighbor, it is going to find the k nearest neighbor of this new data. And then let its neighbor to vote for this new data's belongings. So in this example, it is going to find its nearest 4 neighbor. So in this case, k equals to 4. So it is going to find the 4 nearest neighbors of this new data. And then, so that should be this green point, these three blue point, and it will let these four neighbors to vote for the belongingness of this new data. Because it has three blue points, uh, it has more numbers, more votes than the green group. So this X prime, this new star data should be classified as a blue group. So this is the basic idea of the k nearest neighbor classification. And you may ask how to set k. So k is a hyperparameter. So just like the p in polynomial regression task, so we can use the cross-validation to compare the result and find the k that can provide best performance. And how can we define these nearest neighbors? So we can use the distance measure, like the Euclidean distance or the L1 distance we saw in week 1 or week 2, the L1 norm or the L2 norm that are two distance measurement. And we can also use similarity to represent this nearest concept. So we can choose the cosine similarity, Gaussian kernel, or Laplacian kernel. So if you are, so don't, sometimes we don't care that much about the magnitude or the Euclidean distance between two data points. So we care more about the angle of this data vector, but at the angle difference between the data vector or the angle similarity. So in that case, you may prefer to use the cosine similarity to specify or to define the nearest neighbors. Or sometimes you may prefer to use some weighted vote. Let's say for another example, maybe let me change another color. So maybe there is another green data point here, and now this would be the nearest one of the four nearest neighbor, and we don't want them these four neighbors to have equal vote. We are expecting that the data point that is closer to the new data point would have higher weight on its vote. So in that case, we will use the Gaussian or Laplacian kernel so that the neighbors can provide weighted vote. The closer the data point, the higher the weight of its vote. So that's the different application for this similarity, measure similarity. So you don't need to memorize these equations. You don't need to memorize that. These are just for your information to know that we can not only just compare the Euclidean distance between data points, we can also compare their vector angles. We can also use some we can also make weighted votes based on some defined radius. So this defined radius are specified by these theta parameters. That will be another hyperparameter if you use Gaussian or Laplacian kernel. Okay, and here is a summary about the two variants. for the k nearest neighbor method. The first option is we can let all the neighbor has equal weight. So we simply just count how many neighbors come from like blue group and how many data points come from the green group and just compare their numbers. And the majority will win the this new data point. And another option is we can use weighted vote. So we can use the Gaussian and Laplacian similarity measurement to achieve this weighted voting mechanism. And here is a illustration about this k-nearest neighbor process. So we can see that when setting different k, the belongingness of the new data can be different. So setting up an appropriate value for this hyperparameter k may be critical for certain data. So that is a characteristic for this k nearest neighbor. So the workflow for this one is so it first compute all the similarities between the new data point and all the data points in the provided input. So it will calculate all this distance and then find the top k. So that means find the top k nearest neighbor. So either the top k with shortest distance or the top k with highest similarity measure. And this method is quite different from the, let's say, SVM models we saw. It has no training process. So it's basically memorize all the information about input vectors. It needs to memorize all these locations so that when the new data points come, it can calculate its distance to all these data points. So there is no training at all. So every time the new data point come in, it will repeat this distance computing process. So that would suggest that high time complexity. So it will cost much more time than like SVN or other classification models. So for those models, you will see that the model can generate the prediction almost in like instantly. But for k nearest neighbor, because it needs every time it needs to recalculate those distance and find and sort them and find the top k, it takes time. So if you have learned algorithm before, you will know that this big O notation is representing the time complexity, and this D is representing the time complexity when calculating each distance, each pair of distance. And this n means it needs to calculate this distance n time because it has n data points in the training in the input. So that's why the time complexity is at the level of O and D. Okay. So this would be the k nearest neighbor. And we have finished like all the supervised learning part, like regression and classification. And now it's time to get into the unsupervised learning represented by clustering task. So clustering It's an unsupervised learning method. It's just subfield of unsupervised learning, and it requires data but no labels. So that's why it's unsupervised because well, we don't provide labels for the data. So we only receive data with input features. And clustering is used to detect patterns. It can be used in grouping emails uh, or search results, and it can also be used as like recommendation system. So we group the customer into different categories based on their shopping habits or some certain patterns. And we can also use it in image segmentations. We can use this method to cluster the entire image into several meaningful subregions. So we can divide the entire image into subregions. It is useful when we don't know what we are looking for. Like for supervised learning, we know what we are looking for. We know our expectation is to let the model generate the target variable, right? For like say for house prediction, house price prediction, well, our target is to predict the house. But for this clustering task, uh, most of the time we don't know what we are looking for. We just want the clustering method to process the data and generate some meaningful subgroups based on some unknown pattern or underlying pattern, and then for us to analyze in later stage. But there is a problem for this task. That is, it can get gibberish. So most of the time, it is due to bad feature representation. Um, Sometimes it's because the data has no underlying meaningful cluster structure. Sometimes it's because the dimension is too high. Sometimes it's because the method is or the model is overfitting to the noise or outliers. So there are many factors that can affect the performance of this cluster and generate some result that is not interpretable. Okay, let's see from geometric point of view what we are looking for in the for the clustering task. So given for this example, so the data come with two features, so with income and debt. So with these two features, all these data point can be represented as 2D scatter points, and they are distributed in this 2D spaces like this. But we don't know their belongings or their patterns beforehand. And so what we want is we want to cluster these data points into several meaningful groups. And based on based on what criteria is up to the clustering method. The clustering method would find out what criteria it is going to follow to cluster these data points into different groups. And we can see that these circled groups are the result of the clustering, and that is what we are expecting from the clustering method. And what is the ideal property for these clusters? So um, these groups generated by the clustering model are called clusters. So all the data points in a cluster should be similar to each other so that they can form a same cluster. And the data point from different cluster should be as different as possible. So these two are our expectations for ideal or for the um, output of clustering result. So it represents some ideal expectation from the model. So comparing this case one and case two, which one do you think is a better clustering result?
Two.
Let's see from the chatbot. Yes, the case two is much better than the case one because let's say considering these two criteria. So first one, all the data point in cluster should be similar to each other. So if we look at this right circle in case one, you can see that all these data points spread in a wide range. And in comparison with this with the clusters in case two, uh, these data point, these clusters are more compact than the clusters in case one. And considering the distance, or the difference between clusters, you can see that these two clusters and these two clusters are very close to each other, and they are kind of sharing some area in between. So we cannot say that these two clusters are very different from each other. But in comparison, in case two, these four clusters are well separated. And for the application of the clustering in real-world scenario is it can be used for document clustering. So you may have like a lot of documentation like Word file, text files, and you may have taken like many notes. You can use clustering method to organize them into different topics, maybe. And it can be used in image segmentation task. So it can break up the image into meaningful or perceptually similar regions. So for this one, it just cluster the image pixel into meaningful groups. Say each colors may representing different animals. Maybe the two of them are dogs, and this one may be a cat, I guess. Or it can just cluster the image into foreground and background, like two clusters. And also for image segmentation, it's similar to the previous one. So it can cluster pixels, similar pixels into one region. So it can cluster all the pixels representing the water into this water region, and this grass region, and cloud and sky regions. So it can cluster all these pixels based on the pixel appearance. And of course, considering the pixels local relationship. It can also be used in recommendation engines. Like I said, the system, like YouTube or other apps, may just cluster the users into many different groups based on their patterns or their interest, and then suggest different videos to the different groups just for recommendation. And we can also do some scientific statistical analysis using the clustering method. So for gene expression data, so there are like more than 20K gene, and we can use clustering method to cluster them into different groups. And these groups may representing like certain group of genes that works together or work or representing similar or strong correlated functionality. So we can use clustering method to group them together to give us some insight so that we can do some further analysis inside these groups. Otherwise, if we may be lost in this large amount of data. Okay, this will be about the application of clustering in real-world scenario. Okay, any questions till now? Okay, before we get into the actual k-means clustering method, I think let's have 5 minutes break, and then we get into the actual model that can do this clustering task. So let's come back at 9:02. Hey, let's continue. So for clustering task, we have seen this definition or requirement before. Like for the input, we only require the data samples and with its features. So we have n data points, and each data point comes in d dimensions. So that means it has d features. And we also need to specify the hyperparameter k. That is the expected number of cluster uh, in the output of the clustering result. And the output will be class labels for each data point. So these labels are corresponding to each input data samples. So it specifies the data point belongingness to each group because we specify that we are expecting k clusters as the output. So the labels can only have values from 1 to k. So that's the only possible values for the output. And with this label generated, we can color this we can color the input data point into some meaningful clusters. Okay. And for more, another equivalent definition for that is for clustering task, it is going to partition the total n data points to k disjoint subset. So from subset S1 to Sk. So the important thing is disjoint subset. So translated into plain language is this subset should share no intersections. So they should all of these subsets should share no common data points, and the sum or the union of this subset would be equals to the entire data set. So here are the two constraints we get. So the union of all these subset should be equals to the entire data set. And the intersection between any two subset would be an empty set. That means there will be no subset sharing sharing common data points. So at the end of the clustering task, so each data point in the data set would belong to one of the subset, and it can only belong to one of the subset. So let's look at this example. So for this data set of 12 numbers, and we are expecting to cluster these numbers into two clusters or two subsets. So here is just a sample clustering result. So for S1, it includes 1, 3, 4, 7, 11, 5 points. And S2 includes 2, 5, 6, 8, 9, 10, 12, these 7 data points. So we can see that if we calculate the union of these two sets, that would be equals to the entire 12 data points. So 5 plus 7. So in total, we got all the data points included in this subset. And we calculate if we check the intersection about this S1 and S2, we will see that these two subsets are sharing no common points. And how can we evaluate the clustering result? So we have already got an intuitive feel about the expectation about what is a good cluster result. Like all the data points in a cluster should be similar to each other, and the data points from different clusters should be as different as possible. How can we translate these two requirements into evaluation measure? So that's why this um, Dawn index is proposed. So it involve calculating the intra-cluster instance and inter-cluster distance. So the intra-cluster distance representing the uh, compactness of the cluster, and the inter-cluster distance is representing how different of any two clusters. So we are expecting a small intra-cluster distance and a large inter-cluster distance. So here it comes the Dawn index. So the numerator is the inter-cluster distance, and the denominator is the intra-cluster distance. So we are expecting this inter-cluster distance to be high, but the intra-cluster distance to be low. So that will result in a high Dawn index. So an ideal clustering result would have high Dawn index. So how can we calculate the inter-cluster distance? It's just as shown in this illustration. So we already got the clusters, and the data points belongs to the clusters. So we can calculate the centroid for each cluster. What centroid mean is that is the average location for all the data points belongs to this cluster. So we calculate the centroid for each cluster, and we calculate the centroid to centroid distance for any two of the clusters. And then we choose the maximum distance as the denominator. And for no, we find the minimum one as the numerator for the Dawn index. And for intra-cluster distance, we are going to calculate all the data points, the point to centroid distance within one cluster, and we are going to use the maximum point to centroid distance to represent the intra-cluster distance. So we calculate this distance for all the cluster, and we just use the maximum point to centroid distance as the denominator, and then calculate the Dawn index. And this index will be used to represent the clustering result. And there are also other evaluation metrics like COH metrics. So you can, if you're interested, you can also take a look at that. So with this kind of evaluation metrics defined, we are able to quantitatively evaluate the clustering performance, and so that we can use cross validations to do different experiment and experiment different number for k, and choose the k value that can generate the best Dawn index or COH matrix. So is there any question regarding the evaluation metrics for clustering?
Sorry, can I just clarify? The Dunn index measures how the quality of the clustering solution?
Yes, it is measuring the overall clustering result, like how good
Okay,
the clustering is.
all right. And is it like almost like a percentage or
Um, it is not a percentage because these are just some real numbers, positive real numbers. So there is no like value range for that.
so when in the Dunn index, a high or low Dunn index, how do you know
The
what is good and
high done index means better clustering result.
yeah, so would that be like a 58 or like a 5? Is it depending on the
Yeah, depending on the um, dimension of the data, because you are calculating the cluster distance, and if you have like many features, the dimension would be very high, and thereby the if we are calculating the Euclidean distance, this distance will
okay,
be very high. So there's no like specified value range for that. But because we are doing we we may use um, we are not comparing down index for different data set. I mean, we are not saying comparing the down index of span, uh,
yeah,
s- not span, let's say missing about scenario,
oh, like the music
like two,
radio selection and
yeah,
yeah,
yeah, we are not comparing different uh, uh, data. We are using this down index in the cross validation scheme
okay,
because we are working on the same data. Those down index are comparable for each like for each iteration. So
yeah,
yeah,
okay.
it
I
doesn't
just want
matter if the range is like where if the value is very high or in low range. It doesn't matter that much.
okay. All right, thank you.
Excuse me, Dr. Zen. Can I ask if the distance means physical distance or actually it's kind of like a similarity?
Uh, it's up to you. It's like the k nearest neighbor. We can use the like Euclidean distance, or we can use this cosine similarity or Gaussian kernel or whatever. These are these are all distance definitions. So just like we can use L1 norm, also Manhattan distance or Euclidean distance as the measure of the length. So we can use different measurement to calculate this distance. So this distance is just an abstract term to representing the, let's say, the similarity between the data points and between two data points or between 2 points, because sometimes we are comparing data points to the centroid. So yeah.
Yep,
So the distance can be like Euclidean distance or L1 norm, the Manhattan distance, or the cosine distance for comparing the angle. It depends on your interest or the application field.
clear. Thank you.
But most often we are comparing the Euclidean distance,
Okay, got
the
it. Thank
L2 norm. Yeah. Okay, let's get into the actual logic for this k-means clustering method. So let's see what it is doing step by step. So in step one, we need to choose the number of cluster. So this is specified at the beginning, right? So in this case, we set it equals to 2. So we are expecting 2 clusters as in the output. And then in step 2 is like k random points from the data as centroid. So this we just randomly pick 2 data sample in the input points, and to represent the centroid of the output clusters. And then in next step, we're going to assign all the data points to the closest cluster centroid. So that means, let's say for this point, I need to calculate the distance from this point to centroid C1. And it also need to calculate the distance between the point to C2. And also for other data point, it also need to calculate this distance. And after calculating this distance, we know that which centroid is more closer to each data point, right? So this data point is more close to the C1 centroid. So this data point should be assigned to this C1 cluster. So we do this kind of distance comparison for all the data points and assign all the data points to its closest cluster centroid. So this would be the assignment result. So now we can see that all the data points have been clustered into either right cluster or the green cluster. Because we have more data points belongs to each cluster, the location of the centroid need to be updated, right? So in step 4, we recompute the centroid of newly formed cluster. So because these data points form the red cluster, these data points form the green cluster. So we need to recompute this cluster centroid. So the cross notation that is representing the centroid location for each cluster. And then we repeat step 3 and 4. So step 3 is we assign all the points to the closest cluster centroid. So let's see. In this case, if we reassign all these data points to the new cluster centroid, we need to, let's say, compute the distance again for all the points to the two newly formed cluster centroids, and then do a comparison. So now this time the red point is more closer to the green centroid, and now this time this red point should be belonging to a green cluster in this iteration. So we are doing this reassignment for all the data points based on the newly updated cluster centroid. And now these clusters has been updated, right? Because we have already reassigned their belongingness. And it's time to calculate the new centroid again. It may be here. So we need to calculate the new centroid and then repeat the step 3 and step 4 to recompute to reassign all the data points to the closest cluster centroid and then recalculate the new centroid location. So we repeat this iteratively. But how can we? When will we stop this process? Here are a few stopping criteria for this iterative update process. So we can stop when any one of them meet. We can stop the updating process. So the first one is centroid of newly formed cluster do not change. And the second one is points remain in the same cluster in two consecutive iterations. And we can also set a maximum number of iterations. And when this number is reached, then we stop the clustering process. Any questions regarding this stopping criteria?
Yes, doctor, why is it called k-means? What does it have to be do with mean?
Means this centroid is the average location, so that is the mean of the data point.
So
And
the sorry, yeah.
K is the expected number of clusters. Means this means is the average. So this centroid is the average of this data point's location. So for example, if let's say for this green one, maybe this is one, say one two, and this is two one. This may be three three, and the centroid location would be uh
1 plus 2 plus
1
3
plus 2
divided by
plus
2
3 and
plus 3 plus 1.
2 plus 1 plus 3. And so this is the average of the location. So that is the centroid. So it's corresponding to this means.
So if we can calculate the mean and figure out the centroid, do we have to go through all these steps, 5 steps?
You
Because we
can't
don't have the cluster.
because this is just an intermediate process, and we need to keep updating the centroid locations, because in the next iterations, maybe there will be new data points that is assigned to this cluster. So the belongingness of the data point is not finalized. So we don't know their final belongingness. So so it is a dynamic process. This centroid location is always keep being updated in each iteration. And so here is another point you need to be take care of is these initial locations are set randomly. So we just randomly choose some data points as the initial centroid, and sometimes this different initialization may result in different clustering result. So so that would suggest as we can do some quality check for the clustering result. Let's say we do this we do this clustering process multiple times, but using different initialized centroids, and we monitoring what if there are like large difference on the generated cluster result. If the result has large difference, that means this clustering is not stable. That may suggest that there is no underlying meaningful pattern used for this such clustering. So the clustering is not stable. Okay.
Yeah, thank you.
Okay. So here are other options that you can choose for clustering algorithm. So k-means is just one of them. So it belongs to the flat partition algorithm. That means given the data set, we provide just cluster. So we just do one-time clustering. So we provide the expected k clusters, and then the algorithm will just divide the data into k clusters as the output. So it is just one-time clustering. And we also have hierarchical algorithm. That means we can first divide the entire data set into like 2 clusters. Then for each subset, we can do further clustering. Let's say for this data set, we can do further clustering on this subset. let's say we run the k-means with k equals to 4 to get 4, let's say, subset from as the result. So this is called the hierarchical algorithm. So sometimes you may be interested in some like subtype of if you're doing some like analysis, you may be interested in some subgroups, subgroups, like smaller groups or specific groups inside certain cluster. And in that case, you may prefer to use the hierarchical algorithm because sometimes if you just do this one-time clustering, you may not get the same partition as the hierarchical algorithm. And sometimes the one-time partition algorithm may not work in that case. And you can also choose to use the mixture of Gaussian and spectral clustering. I will leave this tool for you to explore. That is out of the scope of this course. But for this subject, you just need to understand how the k-means performs and how to evaluate its performance. And you understand that you can also do the hierarchical algorithm. So at each level, you can feel free to choose like any flat partition algorithm. Okay. That would be all for the clustering. And in next section, I'm going to talk about the regularization part. So is there any questions regarding the clustering? And so that we can finalize that.
Will we get any k-means clustering problems in the exam?
It will, like all the contents from lecture will be like subject to the final exam contents.
Okay, thanks.
Okay. Next, we are going to talk about the regularization. So regularization is used to reduce the purpose of regularization is to reduce the model complexity so that the model is so that we can avoid overfitting when training the model. So we have seen that using tuning the hyperparameter to choose the optimal hyperparameters that determine the model complexity, like the polynomial regression task. We are setting optimal value for p, which determines the complexity of the regression model. And now we will see another option to reduce the model complexity to avoid overfitting problem. So let's look at this. We still take the linear regression as the example. So we are familiar with that. So the input should be a feature matrix with shape n by d. So that means each data sample come in d dimension, and we have n such data samples, and we provide labels y, that is a real number, and we have n labels corresponding to the n data samples. And the output should be the weighting vector. So this is the vector of size d corresponding to each features in the feature vector. And here is a linear regression model definition. So the prediction could be generated by using the multiplication between the feature matrix and the weighting vector. And to solve this linear regression task, previously we are using the least square regression, right? So we are minimizing the mean squared error. So this XW will be the prediction. Let's say that is Y hat. That is the prediction from the model. And this Y is the true label. So the difference between prediction and true label value, that will be the difference or the error. And we are calculating the squared L2 norm, that is the n divided by n. This would be mean square error, and this is our loss function. And we want to minimize this loss function, and we want to find the optimal weighting vector that can minimize this loss function. And that is how we use least square regression to do this task. And you may have heard of the ridge regression. So the only difference between ridge regression and least square regression is the regularization terms. So the first term is the mean square error, right? It is same as the loss function in this least square regression. So it is mean square error. And the only difference is it is adding this regularization term. So the regularization term is just the L2 norm, the squared L2 norm of the weighting vector, and multiply gamma. That is a hyperparameter controlling the contribution or the weight of this or the strength of this regularization term. And now this overall equation would become our objective function to minimize. So in ridge regression, the purpose is to minimize this loss function plus the regularization term. And it want to find this optimal value for the weighting vector W. So that's the only difference between ridge regression and least square regression. So it is adding the regularization term. And the ridge regression can have analytical solutions. So just like the linear regression, so we can compute this optimal weight vector values by just following the equation. So we don't need to do the gradient descent method to find the optimal weight vector values through iterations. And this is the time complexity for that. And we can see that the objective function now is the loss function of the least square regression plus the regularization term, that is the squared L2 norm. And to get this analytical solution, we just calculate the gradient of this objective function and then set this gradient to 0. If we solve the equation, we will get the W star, that is the solution for ridge regression.
So when would you use this particular type of regression?
For any regression task. So it is another linear regression model, but with regularization term. I will talk about why we use regularization term in later slides. And here is time complexity for the ridge regression, just for your information. So it basically involves the calculation of this matrix multiplication and calculating the inversion of this matrix. Because to find the solution for this W star, we need to left multiply the inverse of this matrix. And so that's why we have two parts. So one for multiplication of this matrix and one for calculating the inversion of this matrix. So this time complexity is just for your information. You don't need to memorize that. So we now know the difference of ridge regression, then why we would use this ridge regression, or why we are going to add this regularization terms. So the first reason is it is easy to optimize. So from mathematical point of view, the squared at L2 norm, because of the squared, it is easy to calculate the gradient, and it provides some mathematical convenience to solve the equations. And
Excuse me, Dr. Sun, can I have a look back to the previous slide?
yeah,
Is this x transpose x, is this actually equals x square?
we cannot say that. Normally, because it is matrix multiplication, normally we don't write like we don't write like x squared. We don't write it in this way. So, but the meaning of it is similar to x squared.
Yeah, got it.
But
Thank you.
it is matrix multiplication.
Yeah,
Doctor,
got it.
sorry, Doctor, could you quickly go through one more time the analytical solution? I think I didn't quite catch that equation.
Yeah. This slide or
Yeah, this slide, analytical solution, W, the first equation.
you don't need to memorize these equations. So just let you know that it has analytical solutions, just like linear regression. So recall that to solve this minimization or optimization problems, we have two methods. One is using analytical solution, and another one is using gradient descent method to find, like, to iteratively update the W value and to slowly decrease the loss function iteratively until we cannot reduce it anymore. That's the gradient descent method. But for analytical solutions, we can get the solution through just the derivation of the equations and find the solutions directly because it is in this quadratic form and it is a well-posed problem, so it is guaranteed to have a unique solution.
The
So
fact that
we
it's
can get the
differentiable
unique
from the-
solution by using the analytical equation. But not all the model have analytical solutions. So that's the benefit of this ridge regression. So not all the model have analytical solutions. So for those models, we need to use gradient descent. We need to iteratively tune the value of W to iteratively update or to reduce the loss function until the loss function reach the local minimum. So it is not guaranteed to get to the global minimum for using the like gradient descent method.
Yeah, thank you, Doctor. If you go back to the next slide, please. That's fine. I'm just curious. What's the I in this equation?
That's the identity matrix. So it is just a
Identity
matrix.
matrix. Okay, yeah.
Yeah.
Gotcha. Okay.
It's like this.
Yeah. Thank you.
Okay. So firstly, the first reason is is easier to optimize because let's say it has two parts, right? Two terms. The first term is the loss function of the least square regression. It is in quadratic form, so it is guaranteed to have a unique solution, and it is well formed or well posed. And the second term, regularization, is also in quadratic form, so it is well behaved. So in combine these two, the entire equation will be like well behaved, and it is guaranteed to have a unique solution. So it has analytical solutions. So that's why it is easier to optimize. So we don't need to use gradient descent method to just slowly update the W vector to get to the minimum of the loss function, or to the minimum of the objective function. So that's the reason one. And reason two is it has better generalizations. So least squares has better training error, but mostly because it may be overfitting to the training data. So if we only consider the training error, it may have like better training error or lower training error. But for ridge regression, it can make better prediction on test set because it is using the regularization term to reduce the complexity of the model. So because it is not overfitting to the training data, so of course, if we monitor the training errors, the prediction on training data, the difference of prediction on training data and the true label of the training data will be slightly larger than the least square regression. So that's why the training error for ridge regression would be higher. But because the trained ridge regression model is not overfitting to the data, it is less complex, and so it has more. Has better generalizability, so it will perform better on test set. So if we visualize their relationship, we can see that for least square regression, the training error, that is the mean squared error, the training error will be the lowest one in comparison with the training error of ridge regression. But when the trained model applied on the test set, the ridge regression model can achieve lower test error than the least square model, because the least square model may have like higher complexity and is more prone to be overfitting, and thereby it may not handle the unseen data as well as the ridge regression. And this is due to the bias variance decomposition. And this is out of the scope of this subject, but I can briefly talk about it. So previously, we know that this is the mean squared error, right? This term is the mean squared error. And previously we have seen how to identify the overfitting and underfitting problems, and through this kind of error curve, right? So there's a turn. This would be let's say test error. This would be the test error. And we have a turning point here, right? This would be the optimal model that will have the lowest test error. Let's see, this is error, and this is the X is model complexity. So we need to choose appropriate model complexity so that through the cross-validation, right? If we keep increasing the model complexity, after a certain turning point, the testing error will start increasing instead of keep decreasing, right? We have seen this curve before when we talk about overfitting and underfitting problems. And on the right-hand side of this optimal vertical dashed line, that would be overfitting. And on the left-hand side, that would be underfitting. And what this bias variance decomposition mean is actually this curve is the addition of two separate curves. So actually it is the result of two curves. So the curves that keep going down is the bias or squared bias. And this curve keep going up. That would be the variance. So that is called the bias variance decomposition. So this kind of test error curve is actually can be decomposed into two separate curves. One is the bias curve that keeps going down, and another curve is variance curve going up. So when model, so what bias or bias square means is this bias is a measure that is measuring the difference between the model's average prediction and the true value. So imagine that we are repeating this. Let's say, imagine that we can repeat the data collection and model training again, and again, and we will have like many different trained models, and each model can have its own prediction for the, let's say, same input values. And what is the difference between all these models' average prediction and the true value will be counted as the bias, and this curve is the bias square. So this measures how far this bias squared curve is measuring how far the average prediction of the model from the true function. So the high bias means high systematic error, and that would suggest an overfitting condition. So we can see that on the left-hand side of this optimal vertical line. So this bias errors are very high, right? So that would suggest a systematic error. That means the model is not complex enough to capture the trend of or the pattern of the underlying data, and it will fall into the underfitting problem. And for the variance, it is measuring the average squared distance of the prediction from their own average. So it measures how much the prediction changes when you train on different data set. So it basically you can think of it as like how stable the trained model would be. Let's say, for example, So we have seen this kind of like true function, and we have sampled some data around it. And so maybe the first time you train, you will get let's say a curve like this. This curve with high complexity. And next time you train on the same data, you may get a curve like this. It shows different shape. And we can see that for this kind of example, it shows high variance on the model prediction, because the first time for this data point, it is predicted as this value. And the next time we train the model, it predicts this value. So there is a large difference between these two times of training. If we repeat it multiple times, we will get this average prediction on such kind of statistics. So it is measuring the variance of this prediction difference if we can train the model multiple times. So the high variance would suggest the model is very sensitive to the training data. And that will also suggest overfitting. So we can see that on the right-hand side of the optimal vertical line, the variance curve is showing high value. And this would suggest overfitting condition. So what we are looking for is a balance between the bias and the variance. And this balance will corresponding to this optimal model complexity. So the ridge regression, what the regularization term doing is it will slightly increase the bias. So it will slightly increase the bias. So let's say we have trained a very complex model at this point. So we slightly increase the bias. That means we decrease the model complexity. Maybe let's just stop here. So we can see the difference is just not that much. We sacrifice a little bit about the bias, and what we gain is a lot of decrease on the variance. So this regularization term is just sacrificing a little bias performance, but gain a lot of performance on the variance of the the variance on the performance prediction performance. So if we keep just doing this moving back or decrease the model complexity, we will reach some balance point that is got a good balance between the bias and variance. Because if we keep decreasing the model complexity, the bias squared measurement will increase much quicker than the decrease of the variance. So it's not worth doing that. So we will reach some balance point, and this balance point would suggest the optimal model complexity. So that is the bias variance decomposition. So this regularization will increase a little bit about the bias, but decrease the variance of the model dramatically. And that's why for the training error, it will get more like for ridge regression, it will show higher training error. That is due to the higher bias, slightly higher bias. But for testing data, the performance is much better than the least square model because it has much lower variance than the least square model. that is out of the scope of this subject. So I will just give you a direction. If you are interested in this concept, you can find more contents related to that. But just give you an intuition or feeling about why this regularization term would benefit the model generalization. Okay. And we have seen this ridge regression is using the squared L2 norm. Can we use the L1 norm as the regularization term? That would be called lasso regression. So we can use that, and it has its own application area and it has its own special benefits. So let's think about some scenario here, similar for the regression task. The y, that is the label, that can be independent of some of the D features. These are the input features. So that means some of the features may be not useful for predicting the value of y. So the features are irrelevant to the our target of prediction. And another fact is sometimes when the dimension of the feature or say the dimension of the input data point is much higher than the total number of samples. Or we can say we have much more features than the data points we have. Let's say for genetic data, we have more than 20K number of features. But maybe for some experiment, we only can collect, let's say, 100 data samples. So in this case, the number of features is much larger than the data set size. So the linear models in this case are likely to overfit. So in this case, it's time to use the lasso regression. So the lasso regression would can be used to select the feature that is relevant to our target prediction variable. And it can also prevent overfitting for large D and small n problems because it is a regularization term. So it will help reducing the complexity of the model and thereby avoid the overfitting problems. So it can solve this problem through these two ways. But how can it achieve it? So this is the lasso regression models equation. So we have seen this terms multiple times. This is the mean square error, right? So we want to minimize this mean square error by finding the optimal weight vector. But here there's a constraint. So under this constraint, the L1 norm of W vector should be less than or equals to T. So this problem is a constraint optimization problem. So what it's doing is, let's say we have let's draw a level set function for the loss function, or for this mean square error function. So the central point, this point will be the solution for this mean squared error term without the constraint. And if we are setting different value for this weight vector, we will get different value for the loss function. So this point is this centroid point is the optimal value for the W. And that means at this point, the loss function will achieve the lowest value. If we keep drawing circles away from these central points, that means each circle is representing weight value set that can achieve same loss function value. And the further the circle, the higher the loss function. So now it becomes a constraint optimization problems. So we keep drawing this loss function value that has larger value until this circle has an intersection point with this feasible set for the weight vector, because this weight vector is under this constraint. So the L1 norm is less than T. That means W1, let's say for 2D cases, W1 plus W2 should less than T. So it is described by this diamond-like area in this coordinate system. So we will see that this level set of the loss function will first reach the corner of this feasible set for weight vector W. And at this corner location, in this case, W1 will equal to 0 and W2 will equals to T. So that means when we doing the prediction, if W1 is 0, that means this, no matter what value we set for X1, this whole term will be totally ignored because the multiplication result will be 0, right? It equals to 0. And we only have this X2 variable left with weight value W2 equals to T. So in this way, using the L1 norm as the constraint, as it is used in lasso regression. So the lasso regression can optimize or push the certain weight value corresponding to irrelevant feature to 0. So for those, it can then thereby doing the feature selections. So for those feature irrelevant to the prediction task, the weight will be optimized to exactly 0, so that the feature value will not contribute to the prediction result. So that means this feature will not be used in the prediction, and in this way, these features are filtered out. So that's how the lasso regression is doing the feature selection. And also because it is a regularization term, and we are going to minimize the entire equation. We are going to minimize the equation. That means we will also minimize the L1 norm of the weight vector. So that means it will not assign like very large values for the weight vector. So in this way, we will reduce the model complexity, and that's how it achieves the second goal. So it reduces the model complexity so that it avoid overfitting for large D and small n problems. And also it will remove the irrelevant feature contributions from the prediction process, and thereby it will also reduce the size of the features it used. So here are the summary for the Lasso regression. So again, it is a convex optimization model. And the optimal solution W star is sparse. That means some of the values or some of the entries in this weight vector can be exactly zeros. And T is a hyperparameter. So smaller T means smaller T here means stronger constraint. And that will result in sparser W vector. So sparser W vector means there will be more zeros in the optimal weight vector. By setting the entries to 0, it will set the contribution of specific feature values to 0, and thereby those features will be filtered out from the prediction process. Okay, and we can see that it is sharing a similar structure as the ridge regression. So these two forms and this one are equivalent. So if you know the optimization task, so the first line is the dual version of the second equation. So they are equivalent tasks. And we can see that in the second form, it is similar to the ridge regression. So the first term is the loss function, the mean squared error, and the second term is the regularization term. So now, unlike the ridge regression that is using the squared L2 norm, here the Lasso regression is using the L1 norm as the regularization term. And here, from so generalizing this Lasso and ridge regression, we can define some regularized empirical risk minimization. It's kind of structure of the objective function. So it is built using two terms. The first term is the loss function, and the second term is the regularization. And we can freely choose what method we use to as the loss function and what method we use for the regularization. So it is a more general format for this type of method. So for example, for this regression, the loss function term, we can use the mean squared error as the loss function. And for logistic regression, we can use this term for that. Although we didn't learn that, but just for your information. So we can use this term as the loss function term. And in this way, this equation will become the objective function for logistic regression. And for SVM model, SVM for regression, not regression, SVM model, we have seen this term before. This is the psi j, the hinge loss. If you find the week 2 slides, you will see this term. So if we replace the loss function term with this equation, now the equation becomes the SVM's loss function. And for the regularization term, we can use the L1 norm, just like the Lasso regression. We can also use the L2 norm, that is squared L2 norm, like the ridge regression. And we can also use the combination of these two. That will become elastic neck. So another difference between ridge regression and Lasso regression is that for ridge regression, if we are minimizing this entire equation at the same time, we also need to minimize this regularization term, right? So ideally, the W vector will become like close to 0 because to minimize the entire function, we need to minimize this regularization term. And the smaller the W value, or the closer the value to 0, the smaller the regularization term will be. So in this way, the ridge regression can reduce the complexity of the model. But the ridge regression or the L2 norm regularization can only send the weight parameter towards 0, but most of the time cannot exactly be 0. But so the ridge regression cannot do the feature selection. It can only be used to reduce the model complexity. But for L1 norm or Lasso regression, it can send or it can optimize certain weight value to be exactly 0, so that it can do the feature selection. So the elastic net that is using both regularization terms, so it has the advantage of both method. So it can limit the model complexity through the L2 norm terms, and it can also do the feature selection through the L1 norm term. So that the elastic neck can take the advantage of both regularization method. And here is a video for the introduction of regularization. I will just leave it to you. So for this regularization part, you don't need to memorize this complex equation, but you need to know the characteristic of L1 norm and L2 norms usage as the regularization terms. For ridge regression, it is using the L2 norm regularization. And the benefit is it can limit the weight value and send the weight value towards 0 so that the model can have lower complexity. And the Lasso regression is using the L1 norm. And because it's using L1 norm, it can send the certain weight parameter to be exactly 0. And thereby, it can remove the feature that is irrelevant to the prediction task. So that's the benefit of L1 norm. So that would be enough as the takeaway knowledge. And also, you understand that for empirical risk minimization, so it is a general form for objective function. So it is composed of a loss function term and regularization terms. for loss function terms, we can use different equations to calculate the loss. Like for linear regression, we are using the mean square error. And for SVM, we are using this psi j term. So that is the term, the relaxation term we talk about in soft SVM. And for regularization, we are free to use the L1 norm, L2 norm, and elastic net. Okay, that will be all for the lecture content. So any questions regarding this part? I know that it is mathematical heavy, but you don't need to memorize the function. You just need to understand their benefits and applicable area. Okay.
Hi, Dr. Zheng. I just asked, you just said we only need to understand their benefits and what. I did not hear the what. Please repeat. Thank you very much.
Already repeat. I already repeat once.
Like you said, we only need to remember the benefits and just that word. I did not
So the
hear.
purpose of this regularization is to reduce the model complexity
Yeah.
through introducing this regularization, right? So
Yeah.
let's say for example, for polynomial regression, we may have x0 plus not x0, w0 plus w1 x1 w2 not x1 x squared plus w3 let's say w15 x15. So this will be a very now in this case p should equals to 15, right?
Yeah.
So this is unnecessary. Let's say this is an unnecessarily complex model, and we want to reduce this complexity. So previously we are setting different value for p, right? So we set p equals to 3 or 5 to reduce the complexity. But now what we can do is we can minimize the weight value. If we minimize this weight value to maybe a very small value, maybe 0.00001, that means this feature can contribute very little. And in this way, we are kind of controlling the freedom of the curve. So the curve will not be very like squiggled like this. So if all the terms all the terms with high order have like very low weight associated with it, the resulting curve will be like close to the curve with lower complexity. It may be like a straight line, or it may be maybe like the x square, something like this. So it can change the complexity of the model by
Okay.
surprising the weight values, right? So we introduce this regularization term, and we want to minimize this regularization term and loss function term together as an objective function. And so in this process, this term will result in a low weight values, right? But for that is for general speaking about what regularization term is doing. But for L2 norm regularization, it will surprise or it will send the value of weight towards 0, but never achieve exactly 0. So it can only set a very low value for the weight, but never 0. So it cannot do the feature selection, but it can reduce the model complexity. But for lasso regression, it is using this L1 term. The L1 term, L1 norm as the regularization term. Using this term can allow certain weight value to be exactly 0. So in this way, the corresponding feature associated with this weight will not contribute to the prediction because let's say if W1 equals to 0, then W1 x1 will be 0, right? If the prediction is W1 x1 plus W2 x2, this will be 0, so it will have no contribution. So this feature is kind of removed. So lasso regression with this L1 norm as the regularization term can do the feature selection. So this L2, this X2 will be the feature selected.
Yes.
Okay. So for elastic net, it is like taking advantage of the both terms. So it is using the L1 norm to do the feature selection, and it can reduce or control the model complexity using the L2 norm.
I see.
Okay.
Doctor?
Yeah.
Sorry, one last thing. So, these are all theoretical concepts along with so many questions that we are going through. I'm able to understand or visualize it, but is it possible to have some example so that, if we try solving it by one example, we'll be able to retain the concept that we are trying to learn here?
What kind of example?
Example as in, if we are like, linear regression, for example, the way we have done using the code, Python code, is it not possible to have a small example to be able to, have a sample training data, like maybe of 4 data points, and then, or if we can find it somewhere?
There are like lasso and ridge regression implementation in the scikit-learn library. So for the lab exercise that you used linear regression,
Yeah.
you can just replace the model with the ridge regression or lasso regression directly.
Okay.
Yeah.
Sure. Thank you.
You can see that they are accepting same parameters, right? So they are just receiving where is it? Here. They are just regression tasks and they are receiving this feature matrix, and we provide the labels, and that's it. And the prediction is the same. So just the feature matrix multiply the weight vector, and that will be the prediction. So everything is same, only the objective function is different. And it is already implemented in the library, and you don't need to worry about that. You just choose the different model name.
Okay. Yep. Makes sense. Thank you.
Yeah. Okay, all good. Okay, so that would be all for today. If you have any other questions, just send me an email, and I will see you all on Friday.
Thank you.
Thank you.
Thanks for
Okay,
coming.
thank you.
Thank you. Bye.
Have a good
Thank you.
evening. Bye.